Hello, I'm David Bonsack, Rheology Product Manager at TA Instruments. I would like to welcome you and thank you for joining us for today's webinar. If you get disconnected at any time, please use the instructions you received to log back in. You can access various content by clicking the Documents widget at the bottom right-hand corner of the screen. This includes speaker bios and additional file downloads. If you need help at any time, click the question mark widget. Our speaker today is Mr. Henri Burhin. He is the Principal Technical Consultant for Polymer Process Consult and an authority in polymer testing with emphasis on viscoelastic property measurements. His expertise includes both plastics and rubber, whether as pure materials or fully compounded. Mr. Burhin has spent more than 30 years in roles within the polymer and rubber industry, principally with Monsanto and Alpha Technologies. He provided technical support with special emphasis on rheological characterization at multinational tire manufacturers and polyolefin suppliers. He is particularly acknowledged for his wide experience in nonlinear viscoelasticity, also known as FT rheology. Henri holds 2 patents, has published many peer-reviewed papers, and has presented his work at several international conferences around the world. The title of his talk is Rubber Process Analyzer for Elastomer and Compound Development and Quality Control. Henri?
Thank you, David, for this introduction, and we're going to start with the presentation, and I'm going to talk about an instrument which is called Rubber Process Analyzer, or RPA. I'm going to discuss the design, the history, and all the experience which have been gained so far on elastomer, compound development, and quality control. Rubber Process Analyzer, this is the presentation outline, and we're going to go through the design and history of the machine. We're going to discuss about the testing scope, elastomer, which means pure gum, rubber compound. And then we will go through a series of polymer case studies and compound case studies. Polymer case studies with average molecular weight distribution, and long chain branching, which are the most important parameter in the characteristic of polymer, and compound case studies including mixing, extrusion, problem like surface aspect, output, grain strength, and thixotropy, which is a very important parameter and characteristic in compound. So the Rubber Process Analyzer, the history and market position. The development of the machine was done actually in the late 80s and the beginning 90s. The commercialization of the product was in 1992, which means that we are something like 25 years of service. The aim and the original aim of the machine was to address rubber processing problems, which was a big problem at that time and still remain a big problem. The original design was actually based on the moving die Rheometer. That means it's a Rheometer where the rotor had been removed and the bottom die is oscillating. The instrument had to retain MDR Q-meter capability. That means it could be able to run isothermal and non-isothermal cure, also monitor sponge compound blowing. Became soon very popular in large rubber factories like tire manufacturers, and actually the RPA was a request of a major, if not one of the biggest tire manufacturer in the world at that time. Much less popular for small and medium-sized companies who found it far too complex to operate and understand. It is true that the instrument requires quite a lot of understanding and basic understanding of physics of flow. And finally, the instrument was rather expensive, especially at that time. The machine was designed to actually cope with the limitation of standard test. So in this case, we're going to see what is the limitation of Mooney viscosity. Everybody knows a Mooney viscosity graph, which is in the slide here. The only problem, of course, is that the Mooney is turning at a constant speed according to the standard ASTM or ISO of 2 RPM. That gives a shear rate of approximately 1.6 second minus 1. reciprocal second. And what is really important, that is the machine is recording a torque rather than a viscosity. Now, when we deal with polymer or compound, the viscosity of this material is depending upon the shear rate which is applied in the test. So with only one rotation speed, the Mooney is not capable of capturing that important parameter. The second most important instrument which is used is the Q-meter, or moving dial rheometer, MDR. Now, that instrument is improperly called a rheometer. We should normally use the term Q-meter rather than a rheometer, and we will see in following slides why we shouldn't do that. But again, in this case, the oscillation of the bottom die, which had replaced the oscillation of the rotor, is done at a constant speed of 100 CPM or 1.6 Hertz. Again, this is 1 point. The standard test which is run with this instrument is isothermal cure or could be non-isothermal cure. The design of MDR would provide the value of in-phase torque and out-of-phase torque, and therefore tangent delta, which gives more information about the compound characteristic. But again, this is a one-point method, and it is important to get more information to help the developer to understand their compound. So, TA instrument RPA and RPA in general, this is a true rheometer. This is a picture of the instrument. Now, the viscosity, and this is something which is important, the viscosity is measured with various types of viscometer or rheometer. A rheometer is used for those fluids which cannot be defined by a single value of viscosity and therefore require more parameters to be set and measured than is the case of a viscometer. This definition is actually coming from Wikipedia. So the standard MDR or ODR which was used is actually not a rheometer. So the RPA, like the MDR, is a machine which is based on forced sine wave oscillation. And that sine wave can be varied in amplitude, or it can be varied in frequency. So the time of the oscillation can be varied, and that will vary the frequency. Now, what is the RPA rheometer and how it compares to open boundary machine currently available in the plastic industry and doing actually the same type of job? So in a frequency sweep, in this case, the RPA can go to 10⁻³ Hertz to 50 Hertz. That's about 5.5 decades, which is really quite remarkable for a machine of that design. In the bottom graph, we see the open boundary DMA, which is the RSG2 geometry, compared to the RPA. The RPA keeps the sample under pressure, which is essential for the vulcanization property of the compound to avoid generation of bubbles or porosity in the compound. But apart of that, it is important to make sure that we measure absolute material property in a closed boundary instrument. So a verification has been done on a PDMS Celipati material at a temperature of 30 degrees C, which is actually the reference material for RS and a TA instrument, a rheological instrument. And as you can see in the graph, it matched extremely well for most of the frequency range, with a little problem in the very low G prime, where actually we can see that the RPA is not as sensitive as the RS, but that is expectable. So absolutely, there is no significant difference between a closed boundary, RPA, and an open boundary on reference material. So what are the typical testing output from a frequency sweep? The first output, which is given by the instrument in a frequency sweep, is actually the measurement of viscosity as a function of frequency. That is really important because now we understand that we can pick up the viscosity dependency to shear rate. So it is much better and more complete characteristic compared to the Mooney. It provides also the value of elastic and viscous modulus versus frequency. In this case, it is a very interesting tool for quality control of polymer, because in this case, on the graph, we can see that G' and G" curve are crossing, which indicates a crossover point. This crossover point is extremely sensitive to very, very subtle variation in polymer quality. So this calculation of the crossover point, which is offered by the RPA, is an excellent tool for quality control of polymer, incoming polymer. The last parameter which is provided by the instrument in a frequency sweep is the curve of tangent delta. The curve of tangent delta is an extremely useful tool for the quality of both compounds and polymer. All these data are coming from one single test. So it is an extremely rich measurement and gives a lot of information about the material. Now, I'm going to give you an example of what is called same or comparable polymers of the same type. So here we have EPDM of the same family, which is the 65 plus minus 5 Mooney units family, having the same amount of ENB, the same amount of ethylene, so the same crystallinity. And we have here 7 different polymers from different suppliers. The suppliers have some slightly different polymerization process, and we can see that, first of all, the viscosity curve versus frequency actually is crossing, meaning they have the same viscosity about at the same shear rate than the Mooney. And this is expectable since they are all from the same Mooney family. But we can see that high frequency and especially low frequency, the polymer are largely different. So that means nobody can expect a polymer giving the same processing characteristic from one and the other. Now, it is to be understood that all these polymers being from the same family, theoretically, a compounder can switch from one to the other and having the same, or expecting they have the same behavior. The second parameter which can be plotted is actually the tangent delta. And the tangent delta is really quite interesting because you can see that here the variation of tangent delta is huge. The property, the characteristic of the polymers are now completely different. And I want to go a little bit deeper in the understanding of the value of tangent delta related to polymer molecular weight and molecular weight distribution. So now we're going just to extract 2 polymers that we are sure of their properties. One is branched, the other one is linear. They have the same Mooney viscosity, and we can see that actually the viscosity curve are crossing exactly at the same frequency or shear rate that it is applied in the Mooney. So these 2 polymers will not be different on a Mooney measurement. Again, there's no chance that these 2 polymers, when mixed, will behave the same in an extruder or in an injection molding machine. In 1997, a company called DSM, which is part now of Bayer, has proposed a special use of this tangent delta value, or delta, which is the phase rather than tangent of the phase, and they are quoting actually the difference in delta or tangent delta at low frequency, 0.1 radian per second, and high frequency at 100 radian per second. The bigger the number, the lower long chain branching would be the polymer. Now, this may be true when you are comparing polymers in the production after polymerization. But for the people who do not know the polymer characteristic in advance, this is extremely dangerous and can lead to very big mistakes that we're going to see now. So, in order to avoid the problem of branching, we started to play with polymers which are known to be linear. So we used polyisobutylene, which cannot be branched. Polymerization does not produce branching in this case, of different molecular weight and molecular weight distribution. Now, you can see on the graph of tangent delta versus frequency that when you go from very low viscosity, very quickly the tangent delta is shooting up, meaning that you achieve a tangent delta which is approaching infinite. That means the polymer behaves like a liquid, like a Newtonian. So we are at the Newtonian behavior region. The further you increase molecular weight, then you are decreasing the curve of tangent delta until you go to the very high molecular weight up to 4 million Dalton, which is the green curve, where actually it's flat. It behaves like a solid. Now you can understand that the delta or the delta tangent delta will not work in this case because the high viscosity would be a more branched polymer, but we know it is impossible on PIB. So further to use this tangent delta, an artificial mix has been made out of 95% of the lowest molecular weight polymer and 5% of the highest molecular weight polymer. And this is the bumpy curve we can see. And this is quite interesting because we can immediately see that the high frequency tangent delta is related to the small molecule because it's very close to the low molecular weight, while at the low frequency tangent delta relates to the high molecular weight. That means with the tangent delta, we have a tool to scan through the entire molecular weight. Now, just to highlight the fact that a test in a frequency sweep cannot differentiate between branching and molecular weight distribution effect, we have made an artificial mixture of all these polyisobutylene in a way that we are artificially making a very broad molecular weight distribution. And we compare that one to a star branch butyl rubber. And we can see that actually these two polymers have exactly the same tangent delta curve. That means it is impossible to differentiate between long chain branching and molecular weight distribution with a frequency sweep. So in this case, the star-shaped butyl is a very particular way of putting branching in a polymer. So now I'm going to go through a series of case studies where we are going to link the polymer characteristic with the compound characteristic in processing. In this case, it's a precise extrusion process, and the problem in extrusion was surface defect, so what is called shark skin. Now, going back in testing the polymer and we looked at the tangent delta, we can see quite a large difference. So we know that it can be either long chain branching or molecular weight distribution. But what is really important to see in this case, and we will see in a minute why, it's what happened at the very high frequency, looking at the very small molecular weight. We developed, and we will see that test a little bit later, a long chain branching test, which is based on large amplitude oscillatory shear, and we applied this. And in that test, we know that with the LCB index, we are able to see that actually the good polymer has the highest level of branching, which is a little bit not really logic. We would expect either the high molecular weight fraction or the branching to give the shark skin in extrusion, but actually not. It's only a molecular weight distribution effect rather than an LCB effect. And this was actually shown as well and explained by Professor Christopher Makosko some time ago. This is another example. Precise extrusion is actually extruding wiper blades for car. And again here we have two compounds, but these two compounds are actually coming from the same producer, but from two different plants. So supposed to be identical, and of course they're not. And we will see in another graph that actually the surface defect which appears in the bed polymer forced the producer to go from 25 meter per minute extrusion speed to 2 meter per minute extrusion speed. And that is of course not acceptable. So we can see that the two polymers are indeed different. So it could be branching, but in this case probably molecular weight distribution. So we ran DSC test on these two polymers, and we can see actually a difference in molecular weight distribution. What is also interesting to see is that on the tangent delta curve, which had been extended by testing at a lower temperature, making a master curve, we have two crossing. And these two crossing are also seen on the molecular weight distribution. That proves that the tangent delta is actually scanning through the molecular weight distribution. But what is really important in this case, the faulty polymer is actually extremely poor in very, very small molecular weight species in the distribution. And actually the small molecules act as a very good, excellent, actually, processing aid. So the polymer which was giving the problem was poor in processing aid, natural processing aid. So that was the source of the problem. The solution was easily found after that. The formulation had been slightly changed in order to give a little bit more processing aid of the right choice, and the new polymer could be used at the same speed. Now, Rheometer strain sweep. This is the second parameter we can play with. So in this case, the frequency remains the same, the time of oscillation is the same, but the amplitude is going to vary from 0.005 degree of arc, which is extremely small. I just want to remind you that the MDR standard is 0.5, up to 360 degree. So now we're going to see a little video which is going to illustrate what is small strain versus high strain on the bottom die. Now this is small strain, and now we can see that the bottom die is oscillating an extremely high strain of about 100 degree of arc. So small amplitude oscillatory shear versus large amplitude oscillatory shear. So what is happening? If we take a polymer and we measure the elastic modulus, for instance, or viscous modulus as a function of strain, we're going to see that at small strain to a certain value of strain, we're going to have a modulus which is independent of strain. That is called linear viscoelasticity domain. In that domain, the oscillation, which is a sine wave, will produce a torque oscillation, which is going to be also a sine wave. So this is the linear viscoelasticity domain. At high strain, we enter into a nonlinear viscoelasticity domain. So in the linear viscoelasticity domain, if we plot then stress as a function of strain, we're going to have a very nice ellipse, which is because both sine wave. At high strain, then what we're going to have is a distorted ellipse. So when we when we apply a strain sine wave, we measure actually a distorted stress wave. And it can be highly distorted. In this case, with polyisobutylene at 1000% strain, which is about 80 degree of arc, we can see that if we apply the red signal as strain, we get the black signal. And we would expect, if it would be linear, the green signal. So we can see that we have a very highly distorted sine wave. Now the problem with a distorted sine wave, we cannot use the same mathematics, and we are looking for a method to quantify the distortion. Our goal was actually to look at a link between the distortion of the stress wave to the polymer characteristic. So the only way to characterize the distortion, or one way, is actually to use a Fourier transform to calculate the higher harmonics of the signal. So it's relatively easy. The function, mathematical function, is quite simple, but basically the distorted sine wave, which is the blue curve, the blue signal, which is a distorted signal, is now divided into a series of perfect stress signal in phase, out of phase of the same frequency, of higher frequency, 3 times or 5 times the frequency. So now we can quantify the amplitude of these all higher harmonics, and because it's a sum of all the harmonics, we sum all these signals, and we come up with the same distorted signal as the experimental. So now we have a correct way to quantify and analyze that. So you remember the different, or the 7 different EPDM of the same family, tangent delta. Now, if we do the test at high strain, we can see that we have also large difference. So we know that we may have large difference in molecular weight distribution, but we have also very large difference in long chain branching. So the graph you have seen before is a Lissajous figure, and we can see easily with the Lissajous figure whether a polymer is branch or linear, but we're missing a mathematical value. So in order to get a mathematical value, an LCB index has been calculated, which is based on ratio of higher harmonics of the real modulus, of the elastic modulus. What you're going to see in the following graph is that we're using AN, but you have to remember that AN equals G prime N and BN equals G double prime N. So the in phase, the real, and out of phase imaginary property. So what we do is we make a ratio of G prime 1 over G prime 5, and this can vary from minus infinity to plus infinity, and we're going to compare that to a rather complex calculation of the ratio of G prime 3 over G prime 5. So when we have the ratio of G prime 1 over G prime 5 larger than E3, which is the calculated value in the bottom, we know that we are in the branch polymer, and that value will be proportional to the quantity of long chain branching. If we are on the left-hand side, meaning the ratio of G prime 1 over G prime 5 is smaller than E3, then we're going to see secondary loop in the Lissajous, and we are now having a linear polymer architecture. Now, this value, is it sensitive to very small level of long chain branching? Yes, it is extremely sensitive, and in fact, based on our experience, we found that it is the most sensitive technique for measurement of very, very low level of long chain branching. So we have made, in this case, a comparison between a branch EPDM and a linear EPDM, and we know that the polymerization process for that EPDM makes linear molecules and can make only linear molecules. And we have made a mixture of 5% of the branch polymer into 95% of the linear one. And we see that immediately the secondary loop disappears. And when we calculate the LCB index, which is the ratio of G prime 1 over G prime 5 minus E3, so when it is negative, that means we are on the left-hand side, we can see that it becomes positive. That means we can detect significantly a different level of branching, and it's only 5%. Now we can apply that to many polymers. We have done tests on all kinds of polymers, including natural rubber. Now this is a case on butyl, meaning isobutylene isoprene rubber, from 2 different suppliers, one from Exxon and one from Russia. We have run a frequency sweep followed by a strain sweep, and we do the analysis in the linear viscoelastic domain. We can see a small difference in crossover point. That means we have significant difference, which could be molecular weight. We can see a difference in tangent delta, So meaning it's molecular weight distribution or branching. Normally, polyisobutylene is perfectly linear, but in butyl, because it contains small level of isoprene, which is a unsaturated polymer, it may contain a little bit of branching due to this insaturation. So in the case of viscosity, we can see already that a very small difference at low frequency on a log scale can produce actually 15% difference on a linear scale. At large strain, we can see immediately that at the higher strain which had been used, which is 90 degree of arc, there is a large difference in tangent delta. That means probably we have actually some kind of branching. So running the Laos test, we can see here that one has very large secondary loop, meaning really linear, and the other one is just losing the secondary loop. If we look at the LCB index, we have some difference, although the Russian one is still slightly negative. The difference may look very small, but it has to be understood that the repeatability of that measurement is really quite high. The LCB index typical repeatability with 95% confidence is plus minus 0.09. So therefore the difference we can see here between the two polymers is significant. It is also interesting to know that between the two polymers there is a very, very distinct way they are picking up oil in mixing. Now, we're going to talk about rubber compound and we're going to talk about troubleshooting. Rubber compound extrusion, serious processing problem in production, and the summary of observation is all batch pass standard QC test. QC test means Mooney and MDR, Rheometer. One batch gave higher extrusion head pressure and temperature, higher swell, and surface defect. It gives something like an orange skin effect, which is suggesting possible scorch in the extruder. So the faulty batch was compared to a trouble-free batch. So the first test which is run is a cure test. So in the cure test we can see that the green curve, the green compound, actually cures or has a longer scorch time. So normally it is supposed to give more scorch safety and should not give any problem in processing. So that was a little bit surprising. So we started to look at non-isothermal cure. Then we saw that there was some difference in the processing characteristic of the compound, of the two compounds, but the non-isothermal cure confirmed that the faulty batch has a longer scorch time. We did a strain sweep going up strain, then back strain, which is characterizing the filler in that case. And that suggests that there's no problem in dispersion. Linear viscoelasticity measurement on the two compounds hardly see any difference except for the tangent delta at low frequency, which is really quite interesting. But when we did Laos, when we are actually measuring the energy lost per oscillation, per cycle. This is according to the ISO standard method, which you can see at the bottom. The energy lost per cycle is actually equals to the surface of the ellipse, or surface of the distorted ellipse, and we can see that actually the bed compound is giving 8% more energy loss per cycle. So it's going to heat much more in the extruder due to the work, and it's going to scorch by shear. So only that kind of test was able to pick up the wrong compound. Also, now it is interesting to analyze what is the effect of linear and branching polymer on compound characteristics. So we took two polymers, one Keltan and one Nordel. Nordel is a linear EPDM, same characteristic as you can see. Nordel is known to be linear and the Keltan is branch. Immediately you can see that on the viscosity we have the same effect as we have seen before. The viscosity at low shear rate for the branch is higher and lower at high shear rate. so it gives more shear thinning. On the tangent delta, we have exactly the same thing, but in this case, it's caused by branching. High strain, the same, and the Lissajous figures, we can easily see that the Nordel, which is linear, gives a secondary loop, while the Keltan is giving no secondary loop. And we can see that the LCB index for Nordel is negative, while the Keltan LCB index is positive. So we can see that also on the G prime and G double prime curve. So now we're going to mix this compound under identical mixing conditions. We keep, of course, the same formulation, which is here. What is important to consider that as soon as you add in a compound some filler, like carbon black or silica, especially reinforcing fillers, what you have is what is called a Payne diagram. So Mr. Payne has done an analysis of what is the contribution of each polymer ingredient into the measurement of modulus. And at very low strain, he defined a G prime 0, meaning 0 strain, and a G prime infinite. Now, one contributor is the polymer characteristic, so the viscosity. The second contributor is the hydrodynamic effect, which is the quantity of filler. And the third one is the in-rubber structure, meaning the interaction between polymer and filler. And then there is a very large part which gives this nonlinear relationship with strain of filler-filler interaction. This filler-filler interaction actually for carbon black is based on van der Waals bonding, on hydrogen bonding for silica. Now these bonds can be broken down by strain, but because they are vicinity type bonds, they can reform on standing. So we can see that as soon as we add more quantity of carbon black, we add nonlinearity. So it is really important when you're testing a rubber compound to be able to go below 0.1%, where actually you reach the plateau of G prime 0. But because this interaction between carbon black or silica is actually vicinity type bond, they are broken down on shear, but they can reform on standing. Most of people ignore that in an RPA or any test like this, when the machine is closing down, you are shearing the material. So therefore, you are changing the property of the material, but not for a long time. It's going to recover. So it is really important that you are controlling the time you're going to program before running a strain test. In this case, in the graph, we can see that a delay from 0.5 to 8 minutes, we have a very large increase because we give more time for the filler structure to reform. Now, this is an example. Also, we have a 15 minutes oscillation at a strain below 0.1% or at 1%. If we do a strain sweep test immediately after machine closure, then we get something which is not acceptable. But if we can wait long enough, we get a perfect Payne diagram with valuable results. Now, what is thixotropy? Thixotropy is actually the property which is given by this destruction of structure between carbon black or silica and the reformation in time. That means the viscosity is going to be decreased by shear or by strain, and on standing it's going to reform, but it's not going to reform in a very short time, and we can study that. Now we're going to see a video which is going to illustrate very, very quickly and easily this phenomenon. The material is actually, looking at the shear thinning, it's a material which has a certain viscosity and has a certain structure. And there is a 7 millimeter steel sphere which rests inside the gel-like material. The structure of the material is high enough to be able to support the sphere. And then now we expose the system to dynamic load due to vibration at 20 Hertz and 1 millimeter. So when we start the oscillation, the vibration, we can see that locally actually the viscosity of the material is reduced and therefore the steel sphere is going down. When we stop the vibration, the speed of descent will slow down, will not stop immediately. That means the viscosity is increasing with time. So that is typically what's happening with a rubber compound. So it is also interesting to note that there's no moving air bubble inside the material. The viscosity actually is reduced by the shear between the sphere and the material. This is exactly what we are illustrating here. Depending on the characteristic of the fillers, we can have a very high and very quick recovery of the structure or very low recovery of the structure. This can be done by looking at strain sweep going upward and downward in the two Keltan and Nordel compound. And we can see that with the branch material, we achieve a better carbon black dispersion, because the difference between the two low strain before going up and coming back indicates a higher dispersion of the carbon black. Now, when we take the two compounds here, we do a cure test and we see that actually the Nordel is giving a much higher maximum torque on the cure curve. This is quite surprising because the Nordel is actually having a lower ENB value. Normally it should give a lower crossing density, but in this case we have achieved a better dispersion of the carbon black, so therefore we have a lower modulus, although the ENB content in the Keltan is higher. So if we now measure the linear viscoelastic properties of the compound, we can see that we still have a higher shear thinning for the branch polymer in the compound. But what is really interesting is when we take these compounds and we extrude them into the same extruder at the same temperature, the same conditions, and we measure pressure and current used by the motor, we can see that actually the Keltan compound, which is the branch material, is having a much lower pressure on extrusion. That means you're going to have a higher output, a better productivity. And the current used by the motor of the extruder is lower as well. We can also see that the temperature of the extruded material is lower with the Keltan as compared to the Nordel. Now, this is another example where we can see a difference in carbon black dispersion or filler dispersion. This is for injection molding compound. We have a few batches and we can see that there are very large difference at the ongoing strain sweep. I just want to emphasize the fact that this is a log scale, so the difference is really very, very large. So the conclusion here of the test is there is highly variable mixing conditions with large difference in carbon black dispersion. So that has highlighted the problem in production. Another test which could have been done on these compounds or batches, different batches, 12 batches, we measure the energy dissipation in process by Laos at 90 degrees of arc at 0.1 Hertz, and we can see that between the lowest and the highest value we have differences about 50%. So this is another source of mixing or extrusion injection problem. There is one thing which is really important when we're running tests, and especially true with RPA. Before we can actually measure properties, we have to make sure that the machine is capable of measuring genuine difference between polymer characteristic or compound characteristics. So in the left column, this is a case of relevant QC. We can see the instrument repeatability giving a coefficient of variation in percent of about 0.75%. is about the same as compound homogeneity, where we have taken 12 samples from one batch of about 300 kilo. So that means the homogeneity of the compound is very good. So production variability, so between batches, 18 batches, we have CVs going from 15 to 5%. Now, we have seen that sometimes the compound homogeneity is so bad that the variability, the CV within a batch, is larger than between batches. Of course, in that case, there's no real need to run a test because any machine would not give relevant conclusion. Actually, this very high variability, low homogeneity compound was linked to the compound that we have seen before with poor mixing conditions. So just to summarize this presentation, so since its commercialization, the RPA has found a growing importance in rubber testing, at first at big rubber manufacturers such as tire manufacturers. It is true to say that the largest number of RPA are in the tire builder laboratory. But it is interesting to understand that it is not only used for research and development, but also for quality control. But these were the most reluctant, these big tire companies, and you know how secretive it can be, to release and share useful information on how to use this novel instrument. The level of complex physical properties of rubber compound and even pure polymers have hindered wide and fast distribution of the machine. Available literature may present some of RPA useful technique in showing how things are different, but often fail to explain why. And this is something which is really important. The rest of the conclusion is not really so important, but what you have to remember is that the RPA is one of the unique instruments where you can see difference, and with this difference explain in the compound why they are different. So thank you very much for your attention.
Thank you, Henri, for that informative presentation. A recorded version of this webinar will be archived and available online through the TA Instruments website. We will now begin the question and answer segment of this webinar. Please submit your questions through the Q&A window. We will do our best to answer as many questions as possible.
All right, Henri, we have questions coming in. Our first question is about tan delta, and the question is, since tan delta is a ratio, would it not be better to look individually at G prime and G double prime behavior to understand the polymers?
Well, no, not really, because you can have values of modulus which are increasing or decreasing. If they're increasing of the same amount, tangent delta will remain the same. But it's really important to remember that tangent delta is actually the measurement of relaxation time of the polymer. And relaxation time of the polymer is an image of the molecular weight distribution on the variation of chain length.
Okay. Our next question is about instrument selection. Can you comment on the advantages or the differences between using, say, an RPA versus an Aries for running louse analysis?
Well, my experience is very simple, especially with highly elastic materials such as rubber. The Aries is irrelevant, mainly because as soon as you exceed a few fraction of a percent deformation, because the test chamber is open, it's an open boundary, you start to have a fracture building into the sample. And therefore, if you repeat oscillation at high strain, you get that crack which is moving towards the center of the sample. And you have a decrease of amplitude of stress. So my experience is that with an open cavity instrument, you cannot run louse test on rubber.
Okay, very good. Let's see. Can you get good information on natural rubber filler interactions? So filler interactions between natural rubber and filler using this technique.
With using louse technique?
Yeah, I think using the louse technique, or maybe if not the louse technique, then maybe you can give some insight as to how you understand natural rubber to filler interaction with the RPA in general.
Well, if you want to really study filler interaction, filler polymer interaction with whatever polymer, it could be natural rubber, SBR, BR, or whatever. Well, of course, what is really important is to consider a pain diagram, so which is a strain sweep. But it is true that by going to high strain, Laos conditions, you remove the effect of filler-filler interaction. And if everything being constant, polymer, quantity of filler, and so on, then you may see difference in interaction between filler and polymer.
Okay. Coming back to another question on the differences between an RPA and an open boundary rheometer like an Aries. In the beginning, there was a diagram comparing the RPA and an Aries. Is there an influence of the film that's used in the RPA?
Based on our experience, we haven't seen any influence of the film on the measurement. But of course, especially for compounds, we cannot really test all possible compounds, because I believe in the world there is an infinite number of compounds. So based on our experience, we haven't seen any influence. But to be sure, both tests has to be run.
Okay. And again, coming to the long chain branching index, is there a theoretical background for the long chain branching index, or is it completely empirical? And if there is a theoretical background, can you comment on what's behind that?
No, it's purely empirical.
Okay. So, and then another question is on gel content in raw polymers. What test parameters or test methods would you use to determine the level or the percentage of gel in raw polymers, such as ESBR?
Well, gel content is it's a little bit difficult to measure. Simply, if you run a frequency sweep and you look at tangent delta, you're going to see immediately if there is a sample of ESBR containing more gel than another one. But there is another consideration, is normally the first step before gel formation is that the material is going to form some branching. And therefore, Laos test is also a good test. But it's not really that easy to be absolutely sure of the quantity of gel by using any rheometer, such as RS or RPA. Okay.
All right, and we have time for just a couple more questions. This is a question about operation. How much training is required for running tests? Is it an easy system to use?
5 minutes.
5 minutes of training. I think that's very tractable for all of us.
Yes, but I would like to comment. You asked the question, how long does it take for training to run a test? You didn't ask the question, how long does it take to understand the test results?
Right. So
that's different, of course.
Some clearly different requirements, and perhaps it's well suited for anyone to perform the tests as long as there's a good understanding for what to do with the data and how to understand the results afterwards.
Yeah, exactly.
Okay. What RPA test configuration is used to compare green strength of mixed rubber, say from room temperature all the way up to maybe 150 F?
You're talking fully compounded stock, or is it master batch?
It says green strength of mixed rubber, so maybe you can...
okay, let's suppose that the compound is not going to cure, because if you want to push the temperature up to 150, it's going to cure. The optimum test for green strength at whatever temperature, usually at extrusion temperature, meaning around 100 degrees C, is a strain sweep test, and you plot S prime as a function of strain. So the higher the S prime at Laos conditions, meaning at high strain, the better the green strength. It's a little bit more complex than that, but this is the typical test to run for green strength.
Okay, so a strain sweep and specifically focusing on the high strain behavior.
And looking at S prime, so the in-phase torque.
S prime high strains. Okay. And then our last question is, how do you analyze a rubber compound mixed in a kneader mixer?
Can you repeat which type of mixer?
Yeah, a kneader mixer. And so maybe how can you analyze the efficiency of the mixing in a kneader mixer?
I would suggest to use a strain sweep on the compound, going from low strain to high strain and back to low strain. This is one of the most sensitive tests for looking at mixing efficiency.
Okay. And would this be what would be referred to as that pain effect test you referred to earlier?
Yeah, yeah.
Okay, perfect. Well, that concludes our question and answer and also today's program. So I would certainly like to thank Henri for joining us today, and I'd also like to thank all of you in our audience for spending some of your day with us. This webinar, like all TA webinars, will be archived and it will be available through the TA Instruments website. And I invite you to look forward for advertisements and invitations to future webinars from TA Instruments. And I thank you all and hope you have a great day.